So I get people asking, at least I got one person asking, and I'm not trying to demonize anybody. Keeps asking me why base 120 when you could use a simpler base like 8 or 12 or 16. Well, the short answer is we can, but the long answer is why stop there? And what I mean by that is, does 12 make a good base? Yes. Does 8 make a good base? Yes. 10, it's a semi-prime. Semi-primes don't typically make the best bases, okay? But see, what 120 really is, more so than anything, is it's a good 100. And if your 100 is base 120, not only is it a good number, but it can be represented in a more simple way. It's like a system within a system. So if we practiced using a mixed radix between 10 and 12, 12 would be kind of like 10 in a way, and 120 would be like 100. Now, you might be asking what's wrong with 144. Well, not exactly anything in particular is wrong with 144 as a square of a base, but 120 is smaller and it manages to have certain characteristics that things like 144 and the standard 100 do not have. One of them is the concept of a fifth, which has highly been, the base 10 has kind of taken over a little bit. And so a fifth is a very common measurement that people typically use on a daily basis. So to completely cut a fifth out of the equation would not be probably the best thing to do. Also, 120 is not able to just represent its factors good. It's also able to represent numbers that are not incorporate into the base, like 11th, I think, for example, or maybe it's a 13th, I don't remember. One of them is 9 and then a symbol for 40 repeating, so it's just 940, 940, 940, or whatever mixed radix you choose to use. You could use a base 12, for example. But the main idea is that a base 120 number system has a simplified representation. So not only is it a highly composite number, but once you master the multiples of 12 and the multiples of 10, a number like 120 is not that difficult to tackle. And if you get used to the associated values of these otherwise random symbols, you can create a very similar intuition that ordinary people have with a base that is 0 through 9 or 0 through 11. We can't necessarily, or probably wouldn't necessarily, be counting several 120s on our fingers. That's mainly the base 12 thing or the base 10 thing. But what we can do, we can count to 120 on our fingers if we wanted to. We would count, we would either count 12 of these, and on this hand, maybe do something like count these like this, and then count them like this or something. That's one thing you could probably do if you really wanted to count to 120 on your fingers. But the point is that this is a really practical number. It has a lot of really practical representations, and I think that it probably makes a better hundredth. And if you have something like an eighth, or a fifth, or a seventh, or a sixth, you could represent this in the base, because each one of these numbers would have a common value, right? If every whole was seen as 120 units, you could look at 8 segments of something, each of representing a value of 15. Or you could see 7 of something representing a value of 17 and a seventh, oddly enough. Base 120 is the 5th factorial, meaning that it actually represents factorials quite well. And the number 144, which is also referred to as a gross, is represented as 2 factorials. Those factorials are the 5th factorial, which is the 1, and then the 4th factorial, which is 24. So it's 124. So it's actually represented as 2 factorials. And if you take all the factorials from 5 down to 1 and add them together, you would get, of course, 153, which is a number that, you know, isn't extremely specific, but it has certain applications if you look it up. It's kind of interesting. But that's the thing. These highly composite numbers make good hundreds. And their squares make good thousands, and their cubes make a great millions. That's the thing about it. So that's one reason why 120, why it makes sense. It's very compact in its representation. And unlike things like 144 and 10, you know, or 100, I mean, 100 has values of 10 just squared. And 144 has values of 12 just squared. They're just squared values of a number that doesn't have a significant, I mean, they do have significant divisibilities, but you can get more for less. You know, you don't even have to go up to 144. You could actually have more for less if you use a mixed radix between 12 and 10. But 10, you know, you just have multiples. You know, 10 just has 5 and 2. So the higher the powers get in base 10, you're just going to have higher multiples of powers of 5 and 2. That's all that's going to happen. I mean, literally, 100 is literally just 5 squared times 2 squared. That's literally what it is. 1,000 is literally 2 cubed times 5 cubed. That's literally what it is. So you want a number that can represent prime fractions, whether the primes are actually in the base or whether they are somewhere close to the base, in such a way that they can be represented with a realistic amount of numbers in the fraction that doesn't result in some type of, you know, some type of over excessive pattern is the idea.